Free training provided by the HVAC School podcast is made possible because of the generous support from our sponsors, Testo, Rector Seal, and Carrier. Now, I'm a huge fan of Testo. I've been a huge fan of Testo for years. I was a huge fan of Testo when the 550 first came out, and we used it, compared it to some competitive devices, and I just fell in love with that product, the Testo 550 manifold. And then from there, they came out with the Testo Smart Probes, and I really started getting more into airflow measurement. And one product that I'm really excited about is the Testo 420 airflow hood. The Testo 420 is really an industry-leading, fully functional airflow hood, and it does a great job in both commercial and residential applications. It has flow straighteners inside of it. It has a high-quality manometer that you can actually detach from the flow hood itself, the Testo 420, and use it separately, which is a great feature. You get a lot of bang for your buck with the Testo 420. It works with the Bluetooth app, so you can actually log a job when you're doing a test and balance on a job. So it just has a lot of really great features. It's very light. It's very easy to handle. That is the Testo 420 flow hood, and I have tried it out. I actually did a video of how to set it up and how to use it on the HVAC School channel. If you want to find out more about it, go to TrueTechTools.com and then just type in 420. Find the Testo 420 on TrueTech Tools. If you want to buy a 420, you can get a great discount by using the offer code GETSCHOOLED in the coupon box that's down on the left side when you start to check out.
Meet Zoomlock, the 10-second flame-free refrigerant fitting from Parker. Reduce labor costs by 60% with no brazing, no flame, and no fire spotter. Discover how Zoomlock can help you be more efficient and productive. Visit Zoomlock.com for more information.
This is the guy who once had to have a bank evacuated because he tested the heat strips during a maintenance. Brian Orr.
Yay, thanks for listening to the HVAC School podcast. I am your host, Brian, and today of all podcasts is the episode to help you remember some things that you might have forgotten or help you to remember some things you might not have known in the first place, but I suspect you probably all knew this at one point in time or another. But usually here's what happens. So you hear something in school, or you hear something from another technician or from in a class or something. It makes sense to you at the time, but then you walk away, and sometimes it's hard to kind of wrap your head around what was said later on when you go to try to remember it. So this is just a quick refresher course. And there are some really practical applications to this, to why this matters. So some of these things are highly practical, and some of them are a little more theoretical. But either way, they'll help you get a good sense of how a run capacitor actually works. A run capacitor is a storage device, and I'm talking specifically about run capacitors, although all capacitors are storage devices. But when we talk about Start Capacitors, they have a little bit different application, and so I'm going to be talking specifically about run capacitors and not Start Capacitors. So with a run capacitor, it's a storage device, and if you were to cut the top off of a run capacitor, and you can do this sometime, take a big copper cutter or something with a wheel on it and cut it open and then take it out, and what you'll find is inside the capacitor, and you can actually hear this, there's oil in it. And that oil acts to dissipate heat, and there are some metal plates, and these metal plates are almost like super thin tinfoil, like the thinnest tinfoil you ever saw, wrapped all around and connected to the terminals. And when I say wrapped all around, it's wrapped in a big spiral inside that capacitor. And most large capacitors, like say you take a 60 microfarad capacitor or an 80 microfarad capacitor, and you unroll it. If you were to take it in the yard and you were unroll it, I think Gray Furnace Man or somebody did a video like this and actually showed this being done. And you unroll it in the yard, you'll see this long sheet of what looks like tinfoil. But if you pay really close attention, you'll notice that it's not just one piece of metal. It's actually two sheets, and they're plastered onto like a plastic insulator that's between them. And so one terminal of the capacitor connects to one plate, and the other terminal of the capacitor connects to another plate. If you look at a dual capacitor is just really two capacitors in one. So it's just two of these circles of tinfoil, of metal, sheet metal, very thin metal, plastered up against each other with an insulator in between. Two of them are jammed into one body, and they share one terminal, which is the C terminal, which that's a whole other topic. Guys get confused. They think that common on the capacitor should connect to common on the contactor, meaning the black side of the contactor, and of course it shouldn't. Common, or C, on the capacitor just means the common point between these two capacitors that are within this one capacitor. So I'm looking here at the top of a dual capacitor, and you've got fan, you've got Herm, and you've got C. And so if you can imagine, this C terminal is connected to one side of both of these capacitors that are inside this one shell, and then the Herm and fan are connected to the opposite side, so the opposite plate. So they don't touch each other. And that's the key thing to recognize when you start to understand how a capacitor really works, is that there's no electrons flowing across that plastic insulating medium. It's just a storage device. So it stores up and it discharges. So there's some common language that we get wrong when we talk about capacitors. We'll say that you feed power into the C terminal and then it goes out of the Herm terminal to the start winding. Well, that's not actually how it works at all, because the electrons that store on the C side, they don't go through that plastic insulation. They designed to go through that. I was about to say they can't go through it, and we'll talk about that later. There are some circumstances where they do go through it, but that's not a good thing. They're not supposed to go through that plastic insulator. So they're supposed to stay on their own side of the capacitor. So when you feed power into the C terminal, it doesn't go across into the Herm or into the fan if you're looking at a dual capacitor. It doesn't go through to the other side. All that it does is that you have these electrons that store on one side, one plate, and then that attracts electrons on the other side. So there's a potential difference across these two plates, and electrons store opposite of each other. There's a force, an interaction force that goes between that plate. And that storage capacity is what we call capacitance, and we measure that in microfarads. So the larger the plates, and then also the distance of the insulation, the distance between the plates, it tells you how much capacitance you're going to have. So those are the two factors. Also, what are the plates made of? So depending on the type of metal they're made of, I think the ones that we use are almost all just aluminum sheeting. So it's aluminum sheeting, it has some oil in it, and it's got some plastic sheeting that goes in between those two sheets of aluminum. So the first thing to know about capacitors is that current doesn't flow through the capacitor. It just goes in and out of the capacitor. If you have two sides of power, let's say you have L1 and L2 of power coming into the bottom of a single phase 240 volt contactor, and you have T1 and T2 coming out the top. So you would connect, in many cases, T1 is going to go to the common terminal on the compressor, right? And then T2 is going to go to the C terminal on the capacitor. This is just, I'm not saying it has to be this way, but this is a common configuration, right? And so what we think is that T2 connects to C, which then feeds through to Herm, and then that powers the start winding. That's actually not what happens. So what actually happens is that from the C terminal, it goes through all the way through the start winding to the Herm terminal. Electrons collect on that plate because of there being a opposite potential, an opposite voltage, opposite sine wave that's applied to C on the capacitor. So we hook that T2 to C, that T1 goes to common, and those electrons move through the motor all the way through the start winding, auxiliary winding, whatever you want to call it, in the motor, and they collect on the other side of that capacitor. And then when that sine wave shifts, when the alternating current goes the other direction, then it shifts back the opposite direction, and it keeps charging and discharging the plate on that Herm side of the capacitor. As you are well aware, not all run capacitors are dual capacitors. So many run capacitors aren't going to be marked at all. They're not going to say C or Herm, and it doesn't matter which side you hook to which, right? And in fact, on some older capacitors, they used to have a marking, and that was the side that you had to connect to the common side. Nowadays, it makes no difference. So the actual inside of the capacitor itself is lined with a plastic insulation, so it doesn't matter which side you hook to C and which side you hook to the Herm side. Again, they're not marked, so there's no markings. It doesn't matter. So if you had one that wasn't a dual capacitor that's got no markings on it, you would just connect one side to the start winding, which would normally, if it was a dual cap, it would be Herm, so you'd connect that to the start winding, save your compressor, and then the other side would go to the top of the contactor, which would often be T2 on the top of the contactor. It doesn't matter which side, as long as everything kind of stays on its own side. The point is that on one side, you're going to one side of the capacitor, and the other side of the capacitor is going to the start winding on the compressor or motor or whatever. And so the way that we tend to think of it is just wrong. It doesn't feed through the capacitor, it stores and discharges, stores and discharges. There's no feeding through that insulating material on the capacitor. The next thing is capacitors don't boost the voltage of the system. And so the reason why people think that a capacitor boosts voltage is two things. First off is that the capacitor has a voltage number on it that's higher than the applied voltage. So I'm looking at a Titan HD little capacitor here right now, and it says 440/370 volts VAC. And so a lot of technicians will say, well, that's the voltage that this capacitor produces. Well, it's not. And so the capacitor doesn't boost the voltage. But we also will observe at times that applied across the capacitor, we will find a higher voltage than what we have applied to the system. So there'll be cases where you apply 240 volts to a circuit, and if you read between Herm and C, say on a dual run capacitor, you'll notice that some cases it's 290 volts or 320 volts or 350 volts, right? You'll notice this higher voltage, and we think of that, oh, that's a higher voltage coming out of the capacitor. And that's what we think. We think the capacitor is somehow boosting the voltage. Now, don't get me wrong, there are circuits that exist in which capacitors are a part of it that do boost voltage. But the typical run capacitor circuit that we use in an air conditioning system is not a voltage boosting circuit. The only reason that you see an increased voltage is because of the counter electromotive force. We can call it counter electromotive force, back EMF, back voltage, whatever you want to call it. There's actually a voltage that is produced by the motor itself. So we have this inductive, because a motor is an inductive load, which means that you have this rotating magnetic field. It's doing kinetic work. The motor is simultaneously spinning because of this rotating electromagnetic field and generating a voltage, a potential as well. And so that back EMF, that opposing EMF, shows up when you measure across the capacitor because it's there in the start winding. Because the start winding, like we mentioned, isn't connected through to the other side of the capacitor. Its only connection is to the capacitor, and so it stores and discharges on that side of the capacitor. So it's kind of, and this isn't technically correct, but if you want to think of like electrons getting stuck there, extra electrons that were generated from the motor, that's a way that you can kind of think of what back EMF is. And so when you're measuring between C and Herm and you see that higher voltage, just know that that higher voltage, that increase, isn't from the capacitor generating it. It's not the power supply doing it. It's actually the motor itself. And so the only time that you're going to see that back EMF is when you have a running motor. That's why you could hook power to a capacitor all day long without any sort of inductive load on it, and you're not going to see an increase in voltage. The capacitor just stores the voltage that's applied to it. It's just that the voltage that's applied between C and Herm is higher because you have this back EMF from the motor itself that's added to that. So that's why you see that, and that does actually tell you something about what's going on with the motor and with the system. And the manufacturers of motors and compressors, they calculate all of this, and that plays into capacitor sizing, it plays into the length of the winding, the size of the winding, all that sort of thing. So that's all calculated for, but that's all why you can measure it. And when you do things like a hard start kit, that's a big factor. That back EMF as well as the applied voltage is a big factor in how you size a potential relay. So a potential relay is a relay that opens up once the back EMF is added in. So once that back EMF gets high enough, that's the way that that potential relay knows that the motor's running up to speed, because as that motor speeds up, the back EMF, the voltage, I should say, the potential that's generated by that motor increases, which opens up that relay and takes the start capacitor out of the circuit. And I'm just highlighting that as another way in which we utilize back EMF or measure back EMF. We're actually measuring it in a potential relay that opens that relay and takes that start capacitor, if you have one, out of the circuit. But again, the capacitor does not boost the voltage. It's not a voltage boosting device. It's literally just a storage device. And in the case of an alternating current circuit, it's storing, discharging, storing, discharging, storing, discharging. But remember, it's not boosting, and no electrons are traveling across from one terminal to the other. There's just storing on the side, the same side that it came in with. So if you think of it like, imagine you have a waiting room, and you have two doors in a waiting room and a wall that splits it right down the center. And so there's a window in between the two, so the two waiting rooms can see each other, and they each have their own door. But when people come in one room and people come in the other room, they can't cross over to the other side of the waiting room. They can just go in and out of the door that they came in with, but they can see the people in the other room. So these electrons can see the electrons on the other side, and that's why they gather, but they can only enter and leave through the same door that they came in on, which is the terminal that they came in on. That's a little way that I think of it. So the next thing is that the higher the capacitance, the higher the current on the start winding. So when you have a typical PSC compressor that doesn't have a hard start kit or any type of start capacitor on it, the only thing in that circuit, the only thing in the Herm circuit, if you're thinking of it in terms of a dual capacitor, the only thing in that start circuit is that capacitor. And so the only way for that start winding to have any current moving through it, and current's just electrons moving through the winding, the only way for current to be going through it is for electrons to be stored and discharged in that capacitor. That's a very simplistic way if you think of it like if you unhooked the start wire. So you took that start wire and you unhooked it off the Herm terminal and you tried to take an amperage on it. Would it draw any amperage? Well, of course not, because there's no circuit, right? If it's disconnected, it's just hanging in the air, there's not going to be any current on the start winding. In the same way that if you have that start wire, so in many cases that would be a blue wire as a real common color for the start wire that connects to the start winding of the compressor, and you have a capacitor that's open, meaning it doesn't have any capacitance. It's reading 0 if you tested it with a capacitor tester. But you still have that wire hooked up, and if you were to take an amp clamp and put it on that blue wire, on that start wire, you would notice that it draws 0 amps, regardless of whether or not the compressor is running. Because sometimes you can get a compressor running even without the capacitor functioning, but without the capacitance in the capacitor, there can be no amperage, no current on the start wire. And so as you increase the capacitance of the capacitor, you will also increase the amperage of the start winding. I say start wire, but the start wire just connects to the start winding on the compressor. So it's the S terminal on the compressor. If you put in too large of a capacitor, let's say it's rated for a 50 and you put in a 60, well, what you're doing is you're creating too much current on the start winding. So you're going to draw more current on the start winding than you should. Now, the compressor overall may read almost the same current or the same current. You may actually see in some cases where you may see a slight drop in your overall amperage on the common wire. But you don't want to carry more current on the start wire, the start winding, than you should. The start winding is an auxiliary. It's a secondary winding, and in many cases it's not as thick, or it's not designed to carry that increased amperage. The bulk of the amperage is designed to be carried on the run winding. Some people will say, well, what about the common winding? Well, there is no such thing as the common winding. On a typical compressor or condenser fan motor or blower motor, PSC blower motor, there's two windings. There's the primary winding, which is the run winding, and then there's the secondary winding, which is the start winding. And the start winding is not designed to carry as much current as the primary winding, the run winding, in almost every case. Some people will say, well, what about three-phase? Well, three-phase is totally different. Three-phase, you actually have three windings. But in a normal single-phase permanent split capacitor application, you have one primary winding, and that's the run winding. And then you have the start winding, which is secondary. It's auxiliary is the term that they often use. And that start winding is completely tied to the capacitance of the capacitor to do any work, to have any current. So if you have an open capacitor that is doing nothing, it's got no capacitance, and you will have 0 amps on the start winding. And if you have a capacitor that is oversized, then you will find that it draws more amperage, more current than it should. A quick little fact about start capacitors. So start capacitors are larger capacitors, so capacitors that have higher microfarad rating, that are left in the circuit for a short period of time and then taken out of the circuit quickly, usually by a potential relay. There's been a lot of different products on the market to do some form of start capacitance. There were PTCRs and other type of start relays that use electronics and all this. But generally speaking, the kind of tried and true method of providing some start assistance is with a start capacitor and a potential relay. So most people, when they choose a hard start kit or a start capacitor, they want a start capacitor and potential relay. Well, my start capacitor and potential relay of choice is a product called Kickstart. Since I started my business 12 years ago, it's been the primary product that we've utilized. And it is a start capacitor and a potential relay. But some people will erroneously call it a two-wire device, because with the Kickstart, you only connect two wires. You connect one to C and one to HRM on a dual capacitor. So you're connecting it across the run capacitor. It's a very simple installation. And so a lot of people think, oh, well, it's a PTCR or some other type of device, and they'll cite certain brands that still use the three-wire setup. It is still a full potential relay and a start capacitor, but it utilizes the voltage across C and HRM, or across the actual start winding, and not from common to the start winding to pull in and drop out the potential relay. And so some people think that that doesn't work, but it's really just it's a sizing thing. So they size the pull in and drop out voltage differently on the Kickstart than they do on some other products. And anything you do with a universal Kickstart, or a universal hard start kit, is going to be somewhat of a guess. You have to kind of figure out, all right, generally speaking, in this range of compressors with this tonnage, what kind of general figure can be used to calculate the size of the potential relay. And the engineers from Kickstart, which is made by RectorSeal, figured out that it was a little more stable, the voltage was a little more stable in between C and HRM on the capacitor itself, as opposed to between HRM and C on the contactor, which is the totally other side, the common side of the compressor. So they calculated that, and so they found some potential relays that are kind of right in the proper range, depending on whether it's the smaller size compressor, so you're under 3 tons or under, or if you're 3.5 tons or over, so 3.5 to 5 tons or 3 below. And so they have the KS1 and the TO5 Kickstart products that are designed for either of those, and I've had great luck with them. But it's important for you to know that it's not the same as the PTCR. There's a lot of different products on the market. Super Boost, you'll see a lot of different products, and they're usually very small, and they don't have a relay. And when they don't have a relay and they're small like that, you know that they're a PTCR product. Not saying that there's no use for them. There's applications where they do work, but in most cases for residential air conditioning, they're not the best product. I would suggest using a properly sized potential relay and a hard start kit, a start capacitor, is the best way to go. And in a lot of cases, the best thing to do is just use the manufacturer's suggested kit. But in some cases, it's good to use a kit that you have on your truck, especially when you've got an older system and you're wanting to get the compressor unlocked, to get a little extra life in it. And we've had really good luck with the Kickstart from RectorSeal. All right, now back to run capacitors. So A couple of the things that you should know about run capacitors. And actually somebody brought this up. Jonathan Oakes in the Facebook group brought this up because I wrote an article about these same topics, just a very brief discussion of it in an article. He said that I should have brought up series versus parallel capacitors. So first of all, you have to know what series versus parallel is. The best way that I know how to describe it is if you think of old Christmas lights. In an old Christmas light, every light, you have two wires. You have two sides to it. And so you can call it hot and common or hot and neutral, whatever you want to call it, in and out, whatever you want to call it. There's two sides, right? You have to have two terminals to make a circuit. You can never just connect one wire. It has to go someplace. And when you're connecting something in series, you're daisy chaining them together. Daisy chain isn't really a good word because some people will use that to describe a parallel circuit. But what you're doing is you're just going in one, out of it, back straight to the other one. So if you imagine, it's like you're just chaining them together directly from end to end to each other. That's just what a series circuit is. Whereas a parallel circuit is you're taking the two wires in and out and you're connecting them one on top of the other. So you're taking the two in wires and you're connecting them together and the two out wires and connecting them together, instead of just taking into one, out of the other, straight into the other one and out of the other. So you're connecting the two ins together and the two outs together instead of connecting the ins to the outs, if you want to think of it that way. Again, if you don't understand what I'm saying, this is kind of a hard thing to describe on radio, but just look up parallel versus series circuits. Just Google that and you'll see how they're connected differently. But if you just think of the old Christmas lights were connected in series. Modern lights and modern circuits are generally connected in parallel. Which if you're going to try to connect two capacitors together to create one larger capacitor, you have to connect in parallel, not in series. So if you say you want to have a 60 microfarad capacitor and you have two 30s, you can very easily do that, but you have to connect them to each other. Instead of going in, out, you just take two sides and connect them to each other and the two other sides and connect them to each other. So you just create two little jumper wires, if that makes sense. It's a very simple setup. It's just parallel connection of capacitors, and then you have a 60 microfarad capacitor at that point. Super simple. If you connect two capacitors in series, so you go in, out, you're actually decreasing the capacitance below that of the lowest capacitor. Say you have a 5 and a 10 microfarad capacitor and you connect them together in series, you're going to have less than 5. And this is the same thing is true when you run series parallel circuits with regular loads. Whenever you connect, like say you took two light bulbs and they were producing a particular amount of watts. So say you had two 10-watt light bulbs and you connect them in series with each other, you're not going to produce double the wattage or double the amperage. You're going to produce half the amperage that you had. So there's going to be half the current flowing through that circuit when you connect them in series versus in parallel. So whenever you want to produce the full capacitance, or if you, for that matter, if you want lights to produce their full lumens value or their full wattage value, you have to connect them in parallel. When you connect loads of any sort, whether they're capacitive or inductive or resistive, in series with each other, you reduce the overall capacity, the overall production by less than the lowest one. So if I hook together an 80 microfarad capacitor and a 5 microfarad capacitor in series, I would have less than 5 microfarads. And I could go through the entire calculation of how to do this, but nobody would remember it. And on a podcast, that's pointless. So you can very easily find information on this by just doing a quick search in Google if you want to know exactly how to do the math. But the fact is that I can't think of any practical reason why you would connect capacitors in series in an HVACR application. If you need to connect them, you're going to connect them in parallel if you need more than one in order to come up with a higher capacitance. And there's some kind of old school applications where they would use a smaller capacitor in parallel in order to create a circuit through the compressor for crankcase heaters. There's some weird applications like that, and that's not what this podcast is about. But there are cases where manufacturers would even connect capacitors in parallel for a reason. But again, it's cumulative between the two capacitors. And then finally, you can test capacitors with the capacitors still in the circuit. And this is, I suggest all my technicians that they do this on maintenances. Now, there are cases where you're going to pull a capacitor out or you already have power disconnected and you want to test a capacitor with the capacitor tester. That's perfectly fine. But I've done a lot of tests between testing with a capacitor tester and then testing it under load. And what you'll find in a lot of cases is that you may have a capacitor that tests good with a capacitor tester that doesn't test good under load, or you even have some cases where it does better under load than it does with the tester. And there's a lot of different reasons for that. I'm not going to get into that. But the main thing to know is a lot of technicians will do this one time. They'll do this test with the run test and they'll say, it doesn't work. Well, it does work. It's science, and it has to work. The only way it's not working is if you're not getting a good reading because of user error, you're not getting your clamp in the right place, you're not doing the math right, or your meter, your actual clamp meter, isn't accurate. And that's very possible. In some cases, when you're doing this capacitor test, you're reading in the lower amperage ranges. So in some cases, under 10 amps. And some meters aren't real accurate when you get under 10 amps. And so that's just a factor of your meter, not a factor of the way that the test works. And so if you have a good quality meter, I've done this a lot with the Testo 770-3 meter that I use, and it works just fine. Again, there's a tolerance there, but we're not wanting to replace every capacitor anyway. We just want to see, is it outside of range? A lot of capacitors are rated plus or minus 5%, plus or minus 6%. But what I generally say is, if it's more than 10% out of range, then you definitely know it should be replaced. If it's kind of in that 5, 6, 7% range, well, then you may want to double check with another meter or whatever. You don't want to go replacing parts that a customer doesn't need. But this underload test is a great way to do it during a maintenance while you're taking your amperage anyway. It's very, very simple. All you do is you take an amperage on your start winding. And so your start winding, it'll often be the blue wire, but it's the wire that goes on a compressor, which is the one that we check most often, but you can also do this on your condenser fan or your blower. It would be the wire that goes to the HERM terminal. So you take that wire that goes to the HERM terminal or to the S terminal on the compressor itself, and you take an amperage of that. And so you find out whatever number that is. Once you have that number, then you multiply that by 2652. Now, many people will say, I heard it was 2650, or I heard it was 2653, or I heard it was 2654. There's all kinds of different opinions about that, but the fact is that it's a long calculation, and I explain it, but 2652 and 2653, it's somewhere in between there is the most accurate. It's, you have to round it. I use 2652 because you can remember that very easily. 52 is double 26. I just remember 26 and 26 times 2 is 52. So 2652. That's how I do it, and it's like accurate within 0.001 or something. It's not going to make any difference in your calculation whether you use 2652 or 2653, but if you want to be slightly more accurate, decimals more accurate, then go ahead and use 2653 if you like. But those numbers are both more accurate than 2650 or 2654. And I'm not sure why anyone uses 2654, but I digress. So that's your multiplier. That's kind of your fixed. And that comes from a formula, which you can find. I actually did an article for the AHR News or ACHR News that you can find that by searching testing capacitors while systems running. So you take that amperage on your start winding, you multiply that by 2652, and then you divide that by the applied voltage across the capacitor. And this is one that I think a lot of technicians get wrong. I think they are often measuring the applied voltage on the contactor, but you actually have to read. So if you're doing the compressor and it's a dual cap, you would go between C and HERM on the capacitor itself. It's the actual voltage applied across the capacitor. It's not going through the capacitor. We already established that, but it's the applied voltage across the capacitor. So that's the inductive reactance added in there. So in many cases, you'll see 270, 280, 290, 300, 320. It'll be a higher number. So you take that amperage of that start winding, you multiply it times 2652, you divide it by the voltage. That gives you your capacitance. And depending on how accurately you take the measurement, it's going to be accurate. In the same way that you could have a meter that's inaccurate on the capacitance reading on the meter itself. It's the same thing. You may have a meter that's just not accurate at the lower amperage ranges. And sometimes start windings don't carry a lot of current. If you're doing a condenser fan motor, for example, you're more likely to be inaccurate with a condenser fan motor or a blower than you are a compressor, just because you're going to have less amperage on the start winding. And so it's going to be a little bit more challenging on those smaller motors. But again, you have a good quality meter, it's not going to be a problem. So that's how you do it, and you can do that under load. I actually did an article on this. If you look at my most recent article, you may be listening to this in the future, but it's from October 17th, 2017, if you look back in the archives, or if you just search capacitors on HVAC School. If you look on the top right of HVAC School, there's a search box there. You can start typing any word, and it will pull up recent articles, and I cover all of these topics. But I also kind of rehash over how to test capacitors under load, and it's a time saver, and you're testing it under the real-life conditions under which that capacitor operates. So checking a capacitor under load is the most realistic way that you are proving the capacitance of that capacitor. It's more accurate than other means because you're using the real voltage and the real operating conditions of that system to test it. And so is a capacitor tester a bad thing with a 9-volt battery on your meter? No, it's a good thing. It's a great thing. But if you have an operating system and you don't want to pull wires off in order to test, then the best thing to do is just do it under load. And once you get quick at it, it takes you a couple seconds to do. It's not a long process. Obviously, you got to pull out the calculator on your phone. So that's the step that takes the longest. So hopefully this has been helpful. I always recommend that you get American-made run capacitors. I'm not paid by anybody to tell you this. We use 2 different brands. We use Titan HD, which is made in Georgia, and then AMRAD capacitors, which are made in Florida. Those are the 2 products that I recommend. They seem to last a lot longer. We've used both of these products for years. More so, we've used the AMRAD product longer. Amrad also makes some interesting products. They have their turbo capacitor that you can use and connect with a bunch of different applications. I don't use it because it's expensive, and so we just keep different sizes on our trucks. But I've been very happy with both of these types of capacitors. A lot of people ask why they fail. Well, the truth is that if you get them improperly sized, then they're going to tend to fail. You see a lot of technicians replace them with the wrong size, and then the next technician replaces it with the wrong size, and it just keeps going. So when in doubt, always confirm data plate on the unit, data plate on the actual component that you're going to. In some cases, someone will replace a compressor or replace a condensing fan motor, and so it may not match the unit model and serial number, so you're going to want to confirm that as well, whether or not the motors or compressor have been replaced. Most manufacturers of those components, if you look up the component data, you'll find the rated run capacitor that goes with it. Obviously, the hotter it is, the more likely they're going to fail. So in very hot environments, hot climates, they're going to be more likely to fail. The way they fail most often is that the metal plates or the insulation or both begin to break down. So when you see a failed capacitor, it can be because there's an issue in the motor, which is creating high current, and then that high current can translate to more heat in the capacitor. That can happen. It's also because of the breakdown of the plates due to the ambient temperature. It can be because the terminals are allowed to short out, or because the terminal was on loose, and so that terminal itself got hot, and then it melted the plastic around the base of the terminal. There's a lot of different things that can cause it, but we also know that the capacitors over the last 10 to 15 years have been having issues themselves. They're just not doing as well as they used to. Some people blame power or fluctuations. There's a lot of different things that can cause issues with capacitors that are related to the power itself, but my experience has said that we have a lot of capacitors that are failing just because the capacitors themselves may have manufacturing issues or something's changed in the way that they're manufactured. But again, when you think of how thin these sheets of metal are inside the capacitor, these plates, anything that causes those to break down where they weren't made to proper tolerances, or the machinery that was making them wasn't inspected as well, then that can certainly contribute to failure. And I'm not saying that's why they do. I don't do autopsies on capacitors, but we have seen a lot more of them fail in recent years, which is why you should use high-quality capacitors. Final thing, I almost forgot to mention this, is that you will see on capacitors, a lot of them have a temperature rating. In fact, I think they all have a temperature rating. And so look at that. This Titan HD I'm looking at has a 70 degrees Celsius rating, which is a very high temperature. And so you'll see some that are lower than that. So the temperature rating on the capacitor matters. A higher number is better. And then the voltage rating, like I mentioned earlier, that matters. That's the point at which the capacitor is rated. It's the rated voltage. It's not how much it produces, because a capacitor doesn't boost voltage. It doesn't create voltage. But when possible, use 440 volt capacitors instead of 370. So you can replace a 370 volt capacitor with a 440. You can't replace a 440 with a 370, but I would suggest replacing 370s with 440s. A lot of technicians thought that, well, if it says 370, I have to replace it with 370, and that's not true. In fact, a lot of manufacturers, like this one I'm holding right now, they'd start to say 440/370, when in fact it's actually just a 440. But they say both just so a technician doesn't think that they can't use it on 370. It's just a kind of way of preventing issues from a technician who doesn't understand how these things work. All right, so that is it for Run Capacitors. Hey, thanks for being a part of the HVAC school community, and it really is a community now. I mean, we have 14,000 people in the Facebook group, over 25,000 subscribers on the Facebook page, and then on the daily tech tip emails, we have 7,500 technicians, business owners, industry insiders who get that, and I'm very flattered and humbled by the amount of people who are consuming what we create here, and it's a testament to our sponsors and their support of us. A lot of people who have helped us along the way. I have to mention Ralph Harmon and HVAC Hacks, HVAC-Hacks.com. Ralph shared the podcast early on and helped to kind of get the word out, and I'm very appreciative to him. I'm appreciative to Dan and Aaron Holohan from heatinghelp.com for participating on the podcast. Jim Bergman with the MeasureQuick app. If you haven't downloaded that yet, now's the time to do it. They're out with a new Testo app-to-app communication update, so check that out. Bill Spohn with TrueTech Tools, TrueTechTools.com. He's been really helpful introducing me to people, giving me content ideas, sending me text messages at midnight telling me about typos in my tech tips, so I really appreciate that. Stephen Reardon, he has his YouTube channel. You can find him on YouTube and find him on Facebook. He's actually out on his own, doing his own thing in business now, so I'm proud of him and what he's got going on. He was a big encouragement, as well as a typo fiend early on, helping me do what I do. Neil Comparetto. Neil was one of the first people who moderated the group. I really appreciate Neil. He has a great video, by the way, if you want to check him out on YouTube, about freezing water in a vacuum. Daniel Anderson, one of the first people to kind of encourage me in the groups, encourage me that maybe a podcast was a good thing to do. And Daniel also helps moderate the group. He's a really good guy. Bill Frisbee, great guy, my entire team at Kalos. There's just a lot of really good people who have supported this along the way, and you are one of them because you are listening to this, and I greatly appreciate it. If you haven't been to the website in a long time, there's a lot of new tech tips being added every day. I'm looking to add some new quizzes here this fall. We're going to do more about gas. You can find that by going to hvacrschool.com. You can find all the podcasts in the Blue Collar Roots Network by going to bluecollarroots.com. So given that it is fall and I'm going on my family fall vacation up to the fall leaf changing capital of the South, which is the Smoky Mountains, I have to do a fall themed dad joke. So here we go. How do you fix a broken pumpkin? Why, that's simple. With a pumpkin patch. Hey, we'll talk next time on HVAC School.
Thanks for listening to the HVAC School Podcast. You can find more great HVACR education material and subscribe to our short daily tech tips by going to hvacrschool.com. If you enjoy the podcast, would you mind hopping on iTunes or the podcast app and leave us a review? We would really appreciate it. See you next week on the HVAC School Podcast.